In this video, we're going to talk about linear and quadratic approximation. So it is often convenient in many different kinds of applications to approximate a complicated function by something that's simpler. Oftentimes a simple function is a polynomial. The simplest polynomial is straight line, so degree 0 would be horizontal line, but non-horizontal lines, degree 1 polynomial. If you want to approximate a function with a linear function, a straight line, it's called linearization or linear approximation. If you want to use a parabola or degree 2 polynomial to approximate a function, it's called quadratic approximation. Those two kinds of approximations we'll talk about today. Later on, if you take calculus 2, you'll talk about degree 3 and 4 and higher degree polynomials. You might wonder why we're bothering, since the computer can approximate whatever function we want to whatever degree of accuracy we want. We don't need linear and quadratic approximation to do that on the computer, and that's okay. So the point here is not to give you a practical way to approximate on the computer. The computer can do these approximations quickly, and it can do a more accurate approximation of the function, and so we can actually see how accurate these approximations are, give us an idea of how good it is to do these things. So let's start out with linearization. We've seen multiple times already that a function is close to its tangent line, if it's differentiable anyway. Close to the point of tangency, the tangent line and the function are close together. So we can approximate a differentiable function, at least, with its tangent line, at least over a small interval. So that's what we're going to do. Linear approximation basically involves using the tangent line to approximate the function. So here's our first example. I want to approximate the cube root of 28 without using a computer or a calculator or something. Now, cube root seems like a fairly simple function, but if you want to compute this by hand, it's a lot more complicated. So I'm going to approximate this cube root function with its tangent line. Now, of course, there's a different tangent line at every x value. Every point of tangency gives you a different line. So which tangent line do we want to choose? Well, there's two different requirements. One, we want the x-coordinate of our tangent line, or our point of tangency, needs to be close to 28, because we're trying to approximate the cube root of 28. And the tangent line is going to be a good approximation for the cube root only when the point of tangency is close here to 28 that we're trying to approximate. And the second thing is we need to be able to find this tangent line easily. So it needs to be simple to compute the function value, that is the cube root, at that particular x-coordinate. So the y-coordinate of the point of tangency, we want to be able to compute relatively simply. We don't want to approximate that, otherwise you're just compounding your error. So we want something where it's easy to compute the cube root and it's not too far away from 28. And the natural choice in this example is 27. 27 is a perfect cube, so cube root of 27 is 3. 27 is 3 cubed. And 27 and 28 are pretty close together. So that's what we're going to do. We're going to base our tangent line on x equals 27. It's going to be fairly simple to compute the tangent line, and yet the tangent line will not be too far away from where we're trying to approximate at 28. Okay, so let's try to go ahead and do this linear approximation. So first I define my function. So here's the cube root. Remember, in Sage there is no cube root function, so you have to use a fractional power. Don't forget parentheses around fractional power. I need the slope of the tangent line, and that will come from the derivative. So that's what I'm going to do next. So here's the derivative of our function f, which is the cube root. I like to call my derivatives df as usual, and here's what the derivative looks like. Now there's one potential pitfall here, because to get the slope, I need to plug in the x value of my point of tangency into this derivative. Now I already decided that computing f of 27, the cube root of 27, was easy to compute. But now I also need to compute f prime of 27. And there's no guarantee that that's also easy to compute, though it's often the case that if f of 27 is relatively simple to find, then f prime of 27 is also, because f and f prime are usually the same kind of functions, and so hopefully f prime of 27 is also easy to find. In this particular example, it is a little messier than f of 27. But anyway, so here's f prime. It's the third of x to the negative 2/3 power. And so I put 27 in there. And 27 to the 2/3, well, 27 to the 1/3 is 3, so this is 3 squared, and that's 9. And then you add a third times a ninth, and you get a 27th. So the slope of the tangent line when x equals 27 is 1/27th. Here's our formula for our tangent line that we've seen several times before. So the function value, x sub 0 is going to be 27. That's the basis for my tangent line. F of 27 is 3, so that's right there. F prime of 27 is 1/27th. I just found that, so there's the slope right there. And then I multiply this by x minus my x value, and that's 27. And here Sage has simplified that to slope-intercept form. So this is my tangent line, 1/27th x plus 2. Now, I'm going to go ahead and just do a graph just as a check. Now, if we were actually doing this by hand without the computer, then we wouldn't be able to do this graph. This graph assumes you can actually plot the cube root. So the blue curve here is the cube root, and the red line is the tangent line. So since we have the computer, I'll go ahead and check and see. So remember, our point of tangency is x equals 27. That's right here. I put a dot there. Here, the tangent line and the cube root function actually agree. They touch there. As you get away from 27, then the approximation gets worse. So the tangent line is still fairly close, but as you get here, say out at 34, you can see there's a definite gap between the tangent line and the function. Now 28, x equals 28 is where I actually want to approximate. And when I look here at x equals 28, on this window anyway, the blue curve and the red line are basically the same. So that looks like this is going to be a good approximation. Okay, so now we got our tangent line. It looks like it's a good approximation. Let's go ahead and use the tangent line to approximate our cube root of 28. And to do that, we're going to use this property that cube root and our tangent line are roughly the same, at least when x is close to 27. So the cube root of 28 is approximately tangent line applied to 28. So I'm just going to put 28 into this tangent line formula here in place of x. So there it is. And I went ahead and used the unsimplified version because it's going to be actually a little easier to use in many cases. So 28 minus 27 is 1. So I get 3 plus 1/27. And there it is. So here's the simplified fraction, 82 over 27, which is roughly 3.037. Okay, so here's the calculations in Sage, if you want Sage to do it for you. Here is Sage's numerical approximation of the cube root of 28. So I just calculated cube root of 28 and converted to a decimal. So compare these two. This is our tangent line approximation, 3.037037 repeating. And here's the actual value, at least to this number of decimal places, 3.03658, blah, blah, blah. So if you round to this third decimal place, this would round up to 0.037. It would actually agree. So these things agree to 3 decimal places. Now, in order to give you a better idea of how far off these are, I'm going to convert this, the error between the approximation and the actual to what's called the percent error. Percent error is, here's the formula for percent error. It's the approximation minus the actual. That's the actual error involved in your approximation. And then you divide that by the actual. These absolute values are just because we don't care if it's positive or negative, so that cancels out any minus sign. And then multiply by 100, that's to convert to a percentage. And the reason we want to do this is because the raw error, just this approximation minus actual, is not always a good representation for how good your approximation is. What this does is compute the error relative to the size of the quantity that you are approximating. For example, if I was approximating your height and I was off by 10 inches, that would be a pretty lousy approximation. If I was approximating the national debt, which is in the trillions, and I was off by $10, that would be basically nothing. So error of 10 doesn't really tell you the whole story. 10 inches relative to your height is a lot. $10 relative to the national debt is next to nothing. And so that's what this percent error is going to do. Give you an idea of how big the error is relative to the size of the quantities being approximated. So here's the percent error in this case. There's the calculation in Sage. Here's the answer. So this is a little over a hundredth of a percent, hundredth and a half of a percent. So that's pretty small. Now, depending on your application, that might be really big. If you're building a space shuttle or something, this might be intolerable. But for many applications, well less than a 1%. This is, not even 2/100ths of a percent would be phenomenal in many cases. Now let's say I wanted to do the cube root of 29, and 29 is still fairly close to 27. There is no other perfect cube that's closer to 29, so we might as well just go ahead and use the same tangent line and see what happens. And so that's what I did. Cube root of 29 is roughly the tangent line evaluated at 29. And so I put 29 in there for x, and I get 83 over 27, which is roughly 3.0741. So here is my my approximation from that same tangent line. Here's the approximation that Sage gives. So this is basically the actual answer, at least rounded to this number of decimal places. And you can see that these are pretty close, 3.072, 3.074. Now we don't have the third decimal place anymore. Remember at 28, if we rounded to 3 decimal places, they were the same. Here we get 2 decimal places, but the third differs. Here's the percent error. There's the percent error calculation. Be careful when you do this in Sage. You get plenty of parentheses. You need parentheses here around the top of the fraction. The approximation minus the actual needs parentheses around it. These parentheses are for function notation. These parentheses are for the absolute value around the whole thing. These parentheses are for the n command, which converts to a decimal. So there's lots of parentheses there. Make sure you get those all lined up right. Okay, so the percent error in this case is almost 600. So remember, before we had less than 2/100ths of a percent. Now we got a little less than 6/100ths of a percent. Still good percent error, though it's gone up quite a bit compared to 28. Here's a graph of the percent error in the approximation. So linear approximation compared to the actual answer that Sage gives us, and I computed the percent error, and you can see that at x equals 27 there is no error because the tangent line and the cube root agree there. As you move away from x equals 27 in either direction, so 28, 29, 30, or if you go this way too, 26, 25, 24, the percent error goes up the further away you get from 27, which is what we should expect. The tangent line is a good approximation, close to the point of tangency. The further away you get from the point of tangency in general, the worse your approximation will become. Now notice though the y-axis here, the top of this y-axis is 1%. So all of this is less than 1% error, which in many applications would be perfectly fine. And in the x direction, we went from 27 up here to 34, so that's 7. And here from 27 down to 20, that's 7 in that direction. So we went 7 units away in either direction, and we're still less than 1% error. Now this is all based on the same tangent line. We haven't changed tangent lines at all. So if you want to approximate cube root of 20 with better than 1% error, you could always try to come up with a better tangent line there. There's no perfect cube near that, but 27 is 3 cubed. The next one down, the whole number cubed would be 2 cubed would be 8, and that would be much further away from 20. But you could try to use some decimals, 2.5 cubed or something, and get closer to 20 if you needed to. Okay, so I want to put all these pieces together now. I did it one by one, step by step, just to kind of show you the concept. Now on your assignment, I'm going to have you do linear approximation. Feel free to copy and paste this block of code and use it on your assignment. Remember, the point here is to see how good these approximations are and get some just kind of general understanding of what approximations are. We're not, the calculations themselves is not the primary point. So feel free to just copy and paste this block on your assignment. You can change the function to whatever function you're trying to approximate. This x sub tangent is the x-coordinate of the point of tangency. On your assignment, I'll tell you what to use. This x sub approx is the x-coordinate where we're actually trying to approximate the function. Make sure you don't get those reversed, otherwise you'll percent error will be wrong in the end. Okay, the rest of it you can leave. So this will calculate the derivative and calculate the tangent line, and then it will print out the approximation from the tangent line. It'll print out the approximation from Sage and give you the percent error. Okay, so feel free just to copy and paste this and use it on your assignment. Okay, so in this example, I'm trying to approximate the sine of pi over 5. In pre-calculus, you memorize a lot of exact values for sine and cosine on the unit circle. That was things like pi over 6 and pi over 4 and pi over 3 and pi over 2. Pi over 5 was not one of those. So we don't know the exact value of that one off the top of our head, but we can approximate it with a tangent line. We want to find a tangent line that's fairly easy to compute, so I'm going to use one of those exact values that I know from pre-calculus. So pi over 5 is not too far away from pi over 6. And from pre-calculus in the unit circle, I remember that the sine of pi over 6 is a half. So pi over 6 comma a half is the point of tangency I'm going to use. And I let Sage do all the work here. So tangent line is based on pi over 6. What I actually want to approximate is x is pi over 5. And then sine of x is the function I'm trying to approximate. Okay, so I let Sage do all the work, and here's what came out. Approximation from the tangent line, roughly 0.59. If I round this to 2 decimal places, this is the right answer, which also rounds to 0.59 if I round to 2 decimal places. The percent error here is almost 0.5%. So in the first example with the cube root, we were off by, even at 29, the cube root of 29, we were off by less than 0.06%. Here, we're almost 0.5%, quite a bit more error involved, and that's just because the sine function is not as straight as the cube root. The cube root function is fairly straight out there by 27, 28, 29. Sine function is not. So here's a graph. Here's our point of tangency where they agree, and as you get away from that point of tangency, they start to separate. Your approximation gets worse. And remember, I had a similar picture with the cube root function, and that graph went out like 7 units in each direction, and the gap was actually smaller on that. And here, I've only gone like half a unit in each direction, and already I have a large gap. So you can see that sine function is not very straight, so tangent line is not going to be great for very long. Here's a graph of the percent error, and again, compare this to what we had with the cube root. Remember, with the cube root, my percent error was less than 1% when I went up to 7 units away. So I was at 27 and I went out to 34 and down to 20, and I was less than 1%. Here, my tangent lines, the point of tangency is based on x equals pi over 6, which is in the neighborhood of a half. And so I've basically gone like a half each way. So much narrower range on my x-axis compared to the cube root, and yet look at my percent error up here over 30%. So linear approximation is not always great depending on the function involved. Now I chose my tangent line to be based on x equals pi over 6 because I knew the sine of pi over 6 from the unit circle and pre-calculus. I also know the sine of pi over 4, that's the square root of 2 over 2. I learned that in pre-calculus as well. Pi over 4 is kind of the next closest thing to pi over 5 on my unit circle. So what would happen if I tried a tangent line based on pi over 4 and did this approximation again, just out of curiosity? So I tried it. Here's my approximation. Here's the exact, or the actual value, more or less, that Sage gives. And you can see that this actually rounds up. If I round to 2 decimal places, this would round up to 0.60, and this is 0.59. So there is more error involved here. It's actually over 1%, so about 1.4% error here. Now, we shouldn't be surprised by that. If you look at the decimal values here, this is pi over 6, pi over 5. That's the thing we're trying to approximate. So we want our point of tangency to be as close as possible to this 0.628. Pi over 6 is roughly 0.524. So that's roughly a tenth away. Pi over 4 is about 0.785. This is about a tenth and a half away. So roughly 50% further away from pi over 5. And the percent error basically tripled. So before we were about 0.5%, here we're getting close to 1.5. So triple the error for another, for that distance in the x direction that we had there. So the closer you can get to your point of tangency, the closer it can get to the place you're trying to approximate, the better you would expect that approximation to be. Okay, well, one way we can improve the approximation other than moving our point of tangency closer is to increase the degree of our polynomial we're using to approximate. Linear approximation uses a degree 1 polynomial. Let's move up to quadratic approximation, which will use a degree 2 polynomial. Graphically, it's a parabola. A parabola bends. It's a curve, and the functions we're trying to approximate also bend. So we would expect these bending curves to, parabolas to match up better than a straight line, which doesn't bend. So let's see how that's going to work. We have our function f of x that we're trying to approximate. We have our tangent line, which we already know how to do that. So here's our tangent line equation. The derivative of the tangent line is this, the slope. Okay, it's a constant. And in other words, the point of tangency, x0 comma f of x sub 0, and at that point, at the point of tangency, the function f and the tangent line at that point have the same slope. Okay, so the tangent line and the original function agree in the function value, the y value. So f of x sub 0 is the y value of the point of tangency. The f and TL agree on that function value. So they have the same y value, and they also have the same slope. So there's sort of two pieces of information that agree. Same slope, same y value, and that's what determines the tangent line. A line is always determined by two pieces of information. So y value and slope here. To do quadratic approximation, we need another piece of information, because to find a parabola, two pieces of information is not enough. So having one point and the slope doesn't uniquely determine a parabola. We need a third piece of information. The natural choice here is to, well, the first, the tangent line, we had first derivative match the function. To get a tangent parabola, we're going to have the second derivative match the function. So to get a tangent parabola, we'll make sure that the function we're trying to approximate and the parabola, they go through the point of tangency. They have the same y value at whatever x we're looking at. They're going to have the same slope, or first derivative, and they're also going to have the same second derivative. And that will determine a unique parabola. Okay, so let's figure out which parabola it is. I'm going to call my quadratic function p for parabola, and I'm going to write my parabola like this. Now normally we'd write a parabola ax squared plus bx plus c, but it's going to be convenient algebraically later, you'll see this, to do a little shift. X minus x sub 0. It's a little just horizontal translation of my parabola. That's going to make the algebra a lot easier. You shouldn't be totally surprised by that shift. It's the same shift we have here in the tangent line. It's a little x minus x0, just a little horizontal translation of the line. So that's what I'm going to do. Our goal here is to find the capital A and the capital B and the capital C that will uniquely determine this parabola we're looking at. Okay, so notice, first off, take our x sub 0. That's the x-coordinate of our point of tangency. That you have to decide. Nothing can tell you what x sub 0 should be. You decide that for yourself, or on your assignment I'll tell you what to use. So you're given x sub 0. If you plug that into this tangent parabola, then everything cancels out except for the c. And that's one of the reasons why I did this little shift by x sub 0. So the c, that last coefficient, is the y value, is going to be the y value of the function. I want p of x sub 0 to be the same as f of x sub 0. Okay, p and f are to have the same function value. That means c has to be f of x sub 0. In that case, f and p will agree at x sub 0, at least. Okay, second fact. Here's the derivative of that. So I take the derivative of that quadratic, no big deal. I'm going to plug in x sub 0 to that derivative, and what comes out is b. So the second reason why I did this little shift by x sub 0 here, to make this simple this way. So p prime of x sub 0, the slope of the parabola at the point of tangency is b. I want that to match the slope of the function there. So b should be f prime of x sub 0. So f prime, if b is f prime of x sub 0, then p prime and f prime will be the same at the point of tangency. Finally, take the second derivative of p, and it happens to be 2a. All the x's are gone by now. So when I plug in x sub 0, I still get 2a. P double prime is a constant. I want p double prime and f double prime to be the same. In order to do that, a needs to be f double prime divided by 2. So when you multiply a times 2, 2a, this 2 will cancel, and you'll get p double prime equals f double prime. Okay? So if I put all that together, here's the parabola I want. The coefficient on the squared term is second derivative of the function I'm trying to approximate, evaluated at x sub 0, that's the point of tangency, and then divided by 2. And then that's times x minus x sub 0 squared. And I'm going to add on f prime of x sub 0, that's the coefficient on the x part, times x minus x sub 0. And then finally add on the c part, which is f of x sub 0. Notice if you cover up this part here, the square term, this is the linear part, this is exactly the tangent line. So the tangent parabola is an extension of the tangent line. It takes the tangent line and it adds on a square term. Okay, let's go ahead and return to our previous examples and see how this works. So let's do the cube root of 28. So I'm trying to approximate the cube root function, so f is the cube root. I'm going to use the same point of tangency I used up above when I did linear approximation, this 27, 3, because that was easy to find. Now I want my tangent parabola, so here's my formula where c is the function value at 27, which is 3. That's my point of tangency, so c is 3. b is f prime at my point of tangency, which is 1/27. I did that before when I did the tangent line. And a is f double prime of 27 divided by 2. And here's the answer. If you want to do it down here, I have the calculation somewhere. Here's the second derivative, and I plugged in 27, I divided by 2. So that's the calculation of a down there. Okay, so this is the tangent parabola. Here's the tangent line. This is exactly the same tangent line I got before, and now I add on this extra square term. Notice that it has a negative coefficient, and if you remember from before, you can look back. The tangent line gave me an approximation that was a little bit too big for x equals 28. This negative square term will subtract a little bit and make the approximation a little bit smaller, and so it's going to get closer to the right answer, as we'll see. So the cube root of 28 is approximately p of 28. I put 28 in there, and what I get is this, and if I simplify that fraction, it's this ugly mess. Here's the approximation of that thing, roughly 3.0366. Okay, here's our approximation from the tangent line, up in example 1, 037, 037, so on. Here's the actual answer, the approximation from Sage, which is correct to this number of decimal places, and you can see that it is, the quadratic approximation up here is better. 03658, 03659. This would round up to, well, this would be 03658. This one would round up to 03659 if I rounded up. So I get a lot more decimal places that that agree. My percent error goes down. All right, here's the percent error in the quadratic approximation, roughly 0.0003% compared to 0.148% from the tangent line. And the tangent line was already pretty good. This quadratic approximation is quite good. Here's the calculation in Sage if you want to see how those calculations work. Here's the graph. So the blue curve, again, is the cube root. The green dotted line is the tangent line that we had before. And the red curve is the tangent parabola, the quadratic approximation. And you can see that close to x equals 27, all three of them are about the same. As you get further away, the blue and the green start to separate quite a bit. The blue and the red stay closer together longer. Notice that I've extended this graph further than was the case with the tangent line, because the parabola follows it longer. Here's the graph of the percent error, and this is the same range on the x-axis as before with the tangent line. X went from 20 to 34. And with the tangent line, remember the percent error went up to about 1% here. Now, 7 units away from the point of tangency, the percent error is less than 0.15%. So we got 0.15% on this whole range of x values. Notice also that close to 27, the error stays very small longer. This is kind of flat here. As you move away from 27, it's really, really small. That much flatter close to 27 than was the case with the tangent line. Go back up if you want and compare that graph. Okay, let's put all those pieces together. Have one last example. The assignment asked you for quadratic approximation, this would be the example to copy and paste. So same setup. You got the function to approximate, in this case sine. You got your point of tangency. In this case I'm going to use pi over 6 again, just like I did before. And pi over 5 is what I'm actually trying to approximate. That's what I want to come out at the end. Everything else you should leave the same. So this will do the derivative and the second derivative and calculate the parabola and give you the percent error. And here's what came out. So this is the percent error from our quadratic approximation of the sine of pi over 5. Roughly 0.03%, 0.03% if you round that up. Compare that to what we got with linear approximation, which was almost 0.5%. So, order of magnitude improvement by moving from a line to a parabola. Here's the graph in this case. And again, when I graphed the sine function with the tangent line, I just went from 0 to 1. Here I've gone out quite a bit further. The tangent line becomes really bad once the sine kind of turns around. You reach this peak and the sine turns around and the tangent line keeps shooting up. At least the parabola does turn. It doesn't turn as fast as sine does, but it starts to turn, so it matches the sine function a lot further. Now eventually the sine function turns around again on this side and the parabola doesn't, so it's not going to be very good for very long over here. Here's the percent error graph. And remember, with tangent line on the same window, x roughly 0 to 1, we had errors that went over 30%, the percent error, and now where I guess it's like 12%, so less than 12%. And again, close to the point of tangency, we got this kind of really flat area where the parabola is quite good here, close to your point of tangency, especially relative to your tangent line. Now, if you want to do even better, the next step would be to get a tangent cubic, or whatever you want to call it, a third degree polynomial. And the idea would be to get the third degree polynomial by using the third derivative. So you'd make the third derivative match, the third derivative of your tangent cubic would match the third derivative of the original function. And you would find that the tangent parabola, just like the tangent line was kind of inside the tangent parabola, just with this square term. To get the tangent cubic, you'd have the tangent parabola in there, and then you'd add on this cubic term. I'll leave that for calculus 2. That's plenty for today. Thanks for listening.